Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about Hess's law. And the way Hess's law works is that you use the chemical reactions of known chemical reactions and known enthalpy changes in order to calculate an unknown enthalpy change for a chemical reaction that is different than the ones that are given to you. So let's jump right into this. This first problem is a kind of an easy problem that's going to cover the basics of Hess's law, and then we'll ramp things up with one that's a little bit more accelerated, and then eventually we'll get to this real practice problem, which is fairly accelerated. So if you watch this video from the beginning to the end, you'll be a pro when it comes to Hess's law. Okay? Now, one of the first things that we need to do Hess's law is we got to learn how to add chemical reactions together. So what I'm going to do is I'm going to add the chemical reaction of A to B and B to see what I get. Okay. So when I add these together, the thing that you need to do is you got to put all of the reactants on the left-hand side. So I got A and B. And then I do the same thing with the products. Okay. I will get B plus C. Now, after you've done that, you're going to cross out like terms. I have B on both sides. And lo and behold, I get the chemical reaction of A to C, and that's the chemical reaction that I'm trying to obtain. Okay, so not all problems work this simply. This is a really easy problem, just so that you understand the basics of Hess's law. There's going to be some things that you have to do in the next problem that might be a little bit more challenging. Okay, but in general, I need you to know how to add chemical reactions together. And we want to add them so that when we get our result, it equals the one that we're trying to find. Now, according to Hess's law, when you add chemical reactions together, you're going to add their enthalpy changes as well. So I'm going to calculate the addition of negative 25 kilojoules with the 10 kilojoules, and negative 25 plus 10 will give you negative 15 kilojoules. So this is the answer for the chemical reaction of A to C is negative 15 kilojoules, but I also want you to see this visually. Okay, so what we're going to do is we're going to create an enthalpy diagram. Now, when we create these enthalpy diagrams, remember there's no x-axis, so you can move left or right however you see fit. Okay, but going up and down is going to be enthalpy. And we're going to take a look at both the chemical reactions that we know. Now, in chemical reaction number one, it says when you go from A to B, there's a decrease of 25 kilojoules. So we want to write that down. When you go from A to B, you're dropping 25 kilojoules. So I'm going to label that as negative 25 kilojoules. This is reaction one, okay? Now, reaction two says when you go from B to C, you increase by 10 kilojoules. So going from B, we'll call this C, there is an increase of 10 kilojoules, okay? And what this question was saying is, well, what if we didn't go from A to B or B to C? What happens if we went from A to C? That's what this question's asking. So if I'm just going to do kind of like a dotted line to keep my value of A at the same spot, well, when we go from A to C, that would be a drop, according to our calculations, of negative 15 kilojoules. But I want you to see how this works out visually. From A to B, the distance was 25, okay? And from B to C, the distance change was 10, okay? But in the up direction. So that means by default, A to C has to be 15, okay? And if you go from A to C, that would be a drop or a negative 15 kilojoules. But if the question was the reverse, what is C to A? Well, C to A would be the same magnitude, 15 kilojoules, but it would be in the positive direction, okay? So this is our first problem. Pretty simple to see if you can kind of understand the basics of Hess's law. And the next question is going to be ramped up just a little bit. And in the next one, you don't have to draw the enthalpy diagram. but you do have to look at chemical reaction 1 and 2 in order to calculate the enthalpy change of a reaction that's not listed as reaction 1 or 2. Okay, so in this next problem, reaction number 1 is A to B, but this time it has an enthalpy change of negative 65 kilojoules. And reaction 2 is going to be 3C to 2B, and it has an enthalpy change of positive 40 kilojoules. And this question is going to ask, I don't want to know the enthalpy change of this. I have it. I don't want to know the enthalpy change of this. I have it. I want to know the enthalpy change of 2A yielding 3C. I want to know the enthalpy change for this chemical reaction. Okay? So what you're going to have to do is you're going to have to do some manipulating of chemical reaction 1 and 2 before you go through the process that I taught you in the first example of adding the chemical reactions together and then adding the enthalpy changes, okay? Because if I add these together right now, it's not going to equal this equation, okay? If I added this right now, it would be A plus 3C yields 3B, and that's not this equation. So we have to do some manipulating. And this is where we have to understand how enthalpy works, okay? One of our properties of enthalpy is that it's an extensive property, and we learned this in a previous video, okay? An extensive property simply means that the amount matters. So if you double a chemical reaction, then you're going to double the enthalpy change, okay? And when I look at this part right here where it says 2A, and I look at these equations, the only place that there's an A is right here, but there's only one A. So I'm going to have to end up multiplying this chemical reaction by 2. And if I double this chemical reaction, then I'm going to have to double the enthalpy change, okay? Let's do that now. So we're going to learn a couple things here in this second example. We're going to learn how to multiply a chemical reaction, and then when we multiply that chemical reaction, we also have to multiply the enthalpy change. So when you multiply a chemical reaction, the only thing that you're changing is the coefficients. So right now, there's 1A and 1B. So if I'm multiplying this by 2, we're going to change that to 2A yielding 2B. Now, if that's the case, then our enthalpy change is going to be 2 times negative 65 kilojoules, which is going to be a negative 130 kilojoules. Okay? So that's what I'm going to do to reaction number 1. I'm going to double it. Okay? Well, what do I have to do to reaction number 2 to make it look more like this equation? Well, I'm going to focus in on this 3C part because the only place that has C's in these equations is reaction number 2. Right here is 3C, but this 3C is a reactant where this 3C is a product. So I think I'm going to have to manipulate this equation. I'm going to have to flip it, which means I'm going to make the reactants products and the products reactants. So I'm going to come over here and write down flip. And when I flip this reaction, this product is now going to be a reactant. And this reactant is now going to be a product. And if I flip the reaction, then I have to flip the sign of the enthalpy change. So this enthalpy change is going to be the reverse of what it was. And the reverse of positive 40 is going to be a negative 40 kilojoules. Now, we get back to the part where I think I've done everything that I need to do to manipulate these reactions so that when I add them together, it equals this. Let's double check through our process of adding chemical reactions together. So I'm going to take both of these. Those are my reactants. So I'm going to do 2A plus 2B. And that's going to yield my products, which is 2B plus 3C. And then I'm going to cancel out any like terms. And the like terms that I have are the 2B. So this actually ends up being 2A yields 3C. That's what I'm trying to do. And that's why I manipulated this one by doubling it and manipulated this one by flipping it, so that when I add them together, my equation is going to equal this. So it requires a little bit of forward thinking here to do these Hess's law problems. Okay. Now that I've added the chemical reactions together, now I need to add the enthalpy changes. And if I add negative 130 plus a negative 140, that's going to give me an enthalpy change of negative 170 kilojoules. So that's going to be the answer to this second problem, this intermediate problem that we're doing. Okay. Now the third problem is over here, and it's in green, so I know that's kind of a little hard to see. So I have it here printed out. So if you want to hit pause and just copy this down and try to see if you can do this problem on your own by manipulating reaction 1, 2, and 3, and then adding them together so that you get your original answer. Okay, that'd be great. And then when you come back, I'll be working on the problem. Okay, so in this problem, we're trying to figure out what would the enthalpy change be if I didn't want any of these, but I wanted to figure out what would the enthalpy change be for C2H4 plus 6F2 to yield 2CF4 plus 4HF. So what I have to do is I have to manipulate each of these equations, okay, reactions 1, 2, and 3, in order so that when I add them together, okay, I'm going to get this equation. Okay, so when I look at reaction number 1, okay, I see this F2, but there's F2s in other places. So if I need to get to 6F2 and it was only this equation, I would think, oh, I have to multiply this by 6. But since I see F2 in other places, maybe I don't. Okay, I think it's more important to look at the HF, because this is the only place that you can find HF. You can't find HF anywhere else. And there's 2 HFs, okay? Well, the only place that has HF is over here, and there's 4. So if there's 2 HFs here, and there's 4 down here, then I think I'm going to have to multiply this reaction by 2. Let's go ahead and do that now. So to multiply this by 2, it's going to be 2H2, 2F2, yielding, so 2, 2, and then this is going to be a 4HF. And if I do that, the enthalpy change is now going to be 2 times negative 537. So 2 times negative 537 is going to be that enthalpy change, okay? And that's going to come out to be negative 1,074 kilojoules, okay? Now let's evaluate reaction number 2, okay? When I look at number 2, I got this carbon, but there's no carbons down here. This F2 is here, but it's also here, so I'm not going to pay attention to that. What's really special about this problem is the CF4, okay? The only place I see CF4s is right here. There's only one here, but there's 2 here. So that tells me that for reaction number 2, I'm probably going to have to multiply this one by 2 as well. So this is going to be a 2, this is going to be a 4, and this is going to be a 2. Let's go ahead and do that. That's going to be a 2, this is going to be a 4, and this is going to be a 2. And what I did is I just multiplied that reaction by 2. So I'm going to have 2 times the negative 680. And 2 times negative 680 is negative 1,360 kilojoules. And I get to reaction 3, our last reaction, and I evaluate it. And I see this C2H4. That's the thing that stands out to me. It's on the product side. But in my practice problem that I want to get to, I want it to be on the reactant side. So I think this is one that I'm going to have to flip. So multiply by 2, and flip. So when we flip this one, it's going to be C2H4 as a reactant. And then these 2 things that are reactants are not going to be products, which is 2C plus 2H2. And that will give me an enthalpy change of the opposite of positive 52.3. So the opposite of positive 52.3 kilojoules would be a negative 52.3 kilojoules. Okay. Now, if I've done everything right, when I add these together, okay, I should get the problem that I'm looking for, because I'm trying to figure out what is that enthalpy change. That's the whole purpose of this manipulation. So let's see if this works out. I'm going to take all of these reactants. There's 5 of them, so you got to be really careful. And I'm going to put them on the left-hand side. Okay, so 2H2, 2F2, 2C, 4F2, and C2H4. Double check that all of those things kind of work out, okay? And then I'm going to take all my products. There's only 4 of them, 1, 2, 3, 4 things, and I'm going to put those on the right-hand side. So 4HF, 2CF4, 2C, and 2H2, and then I'm going to cross out the like terms, okay? So 2H2 cancels out, the 2C's cancel out, and then what we have is we have 2F2 here and 4F2 here, so we're going to add those together, so that's 6F2 plus C2H4 yields HF plus 2CF4, okay? Now, you might say, oh, these things are flip-flopped, okay? It's okay. 1 plus 2 is the same thing as 2 plus 1. So the order in which we add those things does not matter. So we could do this if you want it to match up. And the same thing on the other side, right? We're going to put this to C4 just so that you can see everything lines up perfectly, okay? And just to let you know, I had 4HF right here, so I should have brought 4HF, not just 1HF, so it should be 4HF to make sure everything lines up perfectly. So there was 4HF here, so it should be 4HF here, which should be 4HF here, which should be 4HF here. As you can see, so easy to make a mistake like that, okay? So when you're done, just go back and make sure that you have everything right. So this is the equation that I'm looking for over here. So if when I add the chemical reactions together, according to Hess's law, I have to add the enthalpies together. So in your calculator, you're going to add negative 1,074 with negative 1,360 with negative 52.3. And if you do that, you find out that this is a delta H of negative 2,486.3 kilojoules as an answer, okay? I hope this information was helpful. If you appreciate this type of content, please give it a like and subscribe. Even when you add that comment, it really pushes this information out to other students that are learning how to become pros at Hess's Law.